Good evening, everyone, and welcome to the second meeting of the year. Thank you for being here. Happy Thanksgiving. I know it's we're not getting leftovers tonight, so it could be good. No turkey tonight. Tonight's a very busy meeting. Our theme is students, and Liz Primo, who's our student activity chair, she's away in Switzerland right now, so we're going to have somebody else speak on her behalf. So our theme is students. We have a lot of students here tonight, so thank you for being in attendance. Our chapter invests a lot of time into students, and we do a lot of activities. We comp their meals. So if there's anybody this evening that wants to sponsor students, $35, and that money goes towards the student meals. Just before I start, before this, we had a tech session delivered by Joel Primo. It's always tended well. I don't know if you know who Joel Primo is. Joel, you can stand up. There's Joel. So Joel's a past president, and he's actually developed a series with ASHRAE for HVAC courses. And so he's taken his time to deliver some of these programs for our meetings. And it's just basic HVAC principles. And so you can look forward to that for the next few meetings. Joel's going to be presenting that for us. Now I'd like to welcome the board and the executive. So if board members, if you're here, if you could please stand. Jacob Huff. Jacob's not here. Mike Swain. Celine Baraboo. Peter Shawwood. Joe Delavelle. And Ryan Dickinson, our secretary. Adrian Matani, treasurer. Adam Moons, president-elect. Daniel Redmond, past president and also RBC CTTC for Region 2. And myself, Aaron Dobson, your chapter president. At this time, I'd like to welcome Ryan Dickinson so he can introduce the guests for this evening.
Hi, so the guests for the evening are Don Pearson, Joe Cody, Bianca Filatro, Mark DeMurray, Mackenzie Hunter, Nicholas Lavelle, Zelig Lee, George Peichin, Aditya Patel, Eli Renee, Dennis Stilinski, and Uzo Keje. Thank you.
We have a short list there for tonight, but the new members are Mark Cassani, Chris Hopper, who I think is old returning again, and lastly Dana Versavsky. Thank you.
Like I mentioned, tonight's theme is students. So I'd like to welcome Michael Callahan. He's on the Student Activity Committee with Liz Primo. We do invest a lot of time with student activities, and Michael's here to talk about some of these activities that we do get involved with. So, Michael.
I'd like to start off thanking all the students who managed to come out here tonight, and as well as to all the ASHRAE members who pointed up the dough to help sponsor those meals. It's absolutely crucial. Coming up in our future events, we have a student design team again this year. This year it's something different. We actually have members from the three major post-secondary school boards. We have a student from Algonquin, and I believe two from Ottawa-Valley, and as well as a student from Carleton. And this year their mentor will be Joel Primo, but if there are any other members who wish to lend assistance, it would be greatly appreciated. Just please let myself, Elizabeth, or Jason Purcell know. Coming up in December 6th, the Student Activities Group will again be taking a group of high school shop class students from the Orange School to Modern Niagara's shop. Again, Student High School was actually really pleased with this from last year with Elizabeth, and it's just a great chance to get these students out there to actually see real world, not a more educational environment, and to show that there is more to, to see what an actual shop model class looks like, and that there are more apprenticeship programs besides the plumbing and electrical that we see Further off, again, we will be running a career fair. This will be championed by Jason Bursell and Chris Habits. And as well, I'd like to thank the students from the stage app for putting on their tabletop tonight. Greatly appreciated. If anyone would like to come up and perhaps give us all a quick explanation of it. Yes?
Hello everybody, my name is Nicholas, and this is a project we made for high school students to be more interested in our program. So this is basically a heating or cooling system we use with hair to like understand how the heat transfer from water to hair and everything like that. So we basically use either water or hot water or cooling water. So one of these we can put one of the coils, we put water, hot water, and we pass air through it. We have a different temperature out of it, so we can already see the difference in the temperature. And basically the objective of this project is to find the CFM of it after all. We use the BTU of it with the calculation with the 500 multiplied with the US gallon multiplied by the differential temperature. So that's basically the project we made for the high school student. So yeah, so we later want to do some more testing with cool water. So if you guys want to see it, we're going to explain it that we're specifically with this cooling. Thank you.
Just one thing to mention, this year will be the second annual student scholarship purchase that's going to be awarded. The deadline is this December, so if you do log on to the ASHRAE website, it's for a student in the second year can apply for this bursary, and we will be giving them this $3,000 scholarship near the end of the year. And also another thing that we are doing with the students this year is our chapter is teaming up with the MCA, and we're being involved with the OCA Symposium and Trade Show at the EY Center. So this February, we have a booth that we're putting together. It's all geared towards high school students, and it's more of a hands-on approach. We're teaming up with a lot of different companies within our industry, and putting on a lot of displays to kind of showcase our industry to the students. With that said, October and next month is very busy. There's a lot of events that we have put on. So I'm going to invite a few people up right now to talk about these various events. But before I do that, I'd like to get Adam Moons to talk about research promotion and what we're raffling off for tonight. Oh,
I have a question.
Yeah.
The scholarship is available for college students or for...
I believe St. Jeff, we'll have to check on that.
I don't think St. Jeff is included in that.
Okay,
But I think I'll double check and I'll let you know.
yeah, we'll send it an email. No, you will.
Thanks, Aaron. Once again, the focus at the beginning of the ASHRAE year is thanking our donors, the generous organizations and individuals who sponsor ASHRAE research. Also, we look to raise awareness regarding the benefits of your contributions. At present, there are nearly $1.2 million in research operational in Region 2 alone. This includes 3 allocations to Carleton University as well as the NRC. So the monies that are being raised by things like our raffle tonight are very much staying within our zones and are helping us to realize things that influence a sustainable community and furthering the careers that we all get to enjoy. The Ottawa-Valley chapter this year is initiating an endowment for the purpose of continued support of the YAY Leadership Program. We've been great supporters of this program for quite some time now, and what we're going to do is going to foster the growth of that and the furtherance of it for many years to come. So the endowment is going to be a $10,000 endowment for the next 3 years. $30,000 that's going to be goes towards our RP contributions, and it also comes back as realized monies for a lot of our young members to experience what many have already done. And for myself, for Joe, there's a lot of people who have had the opportunity to be a part of it, and it's very valuable. So we're very proud to be able to do that. The OVC legacy is continued support of these initiatives. All the monies that we're putting in, all the monies that we raise, and how we champion these causes is something that Ottawa-Valley chapter should be very proud of. We're far ahead of the bar when it comes to not just our region, but society at large. We put more dollars per capita in, and I think that we're seeing the benefits in great program, in great attendance, in great support from the top on down. To date, we're at over $11,000 of our goal of $34,600 for the year. This is a great thanks to our chapter and to the generous contributions from all of you raised last month from the tickets that Ainsworth was able to give us for the Red Blacks. This month there are 2 tickets still available if anybody got missed by me. 2 tickets to the Senators versus the Red Wings, plus parking passes. $20 gets you 5 opportunities for that glorious prize package. So please see any one of the BOG or the executive if you're still looking to get tickets. And yeah, that's on the 23rd. We're going to have more detailed updates and recognition going to be posted in the meetings to come. And thank you all very much for your generosity in research promotions.
So for a few events, one event that happened a few days ago, which was the Stroke Play Golf Tournament. And there was a big shocker there. We got a newcomer that's a pro golfer from out of town that won this tournament. And I'll have Joe Delabelle talk about this event. And also about our first GA event this year.
Hi everyone. So as Aaron mentioned, we had our stroke play event on Friday of last week. We had 22 people come out. So if you're here tonight, thank you very much for participating. It goes a long way. So without further ado, I'd like to announce the champion from last Friday is Trevor Thompson. He shot a 78, which is very impressive. And he was actually the one who bought the trophy, so yeah, I'd like to throw a thank you to him too. While I was on vacation, he stepped up and really helped me and booked a lot of things for the course, so thank you, Trevor, for helping with that as well. So next year again, let's try to get him down from the top, and maybe I'll get a swing that's worth as much as 78, but very good score, man, congratulations. So Jordan's not here tonight, but changing over to YEA, Jordan has booked 18 tickets for the 67s game next 2 Fridays from now, so October 25th. If you are a member, it's $10, and if you're a non-member, it's $20. So all you members that look young that I see in the front here, in the back, and students over there, feel free to come out. If you guys have questions, just come see me after. Like, it's a very casual event. We'll probably go meet up somewhere in the on Bank Street before to grab my tea. So if you're interested, it's a really good way to meet other members. And yeah, it's really good for participation too, so we keep doing events like this. So any questions, let me know, and thanks again for your support.
Another marquee event that we have every year is our ASHRAE bowling tournament. And I get Michael to come up and talk a bit about that.
So we are looking forward again to planning the tournament. We are hoping to host this at Maryville Bowling Lanes. We're just waiting for confirmation, but as now we're looking towards Wednesday, November 27th. If anyone has any conflicts or wish to propose an alternative date, just please let me know. Thank you.
We're getting through this list here, we're almost done. One new thing for our chapter, and this is kind of head up by Adrian and Celine, is we're starting Women in ASHRAE, a networking event. And our first event's coming up, so
because there are more women in our chapter, and we'd like to just highlight them and support them. So we're just trying to put together a social event that's coming up this October 20, sorry. I can't find the date right after I found it. It's October 24th, it's a Thursday. It's going to be at the Clock Tower in Westboro. It starts at 5:49. It's a networking event, so come whenever you can. Please forward it to any women that you know in your office or in industry. We're just looking to bring out women in industry, talk about our experiences, like trying to build up the conversation. The entire purpose of the Women in ASHRAE committee and the events is just to start a conversation, talk about what we can do to make women more inclusive into the industry, and we're going to try and open it up to men eventually, but we want to just start reflecting on who is in the industry, what our history is, and what we can do to support each other. So if you do know anyone, again, if you can please send it out. We're trying to see who's out there in the industry and trying to connect all of us together. So we can connect. Thanks.
The last thing is tomorrow we have our first seminar this year. I'd like to get Jacob to come up and talk about it. There's a few spots left, and anybody's interested in attending this seminar, it's tomorrow. It's a full day event, but Jacob or Trevor will have some more details on that.
Hello. Seminar tomorrow is on air system fundamentals, and Ryan McGilvery, tonight's speaker, will actually be the one presenting. There's a few spots left, and I want to say thanks to the Masters Group for hosting it. It does include breakfast, lunch, and your fundamentals handbook. A couple spots left. Register online and enjoy it. It's a great course where you will learn a lot.
That said, that concludes our business session for this evening. We'll start dinner service and reconvene with the raffle draw. And we'll start with the presentation for this evening from the ASHRAE Distinguished Lecturer, Mrs. Ryan McGilvery from Saskatoon. So enjoy your dinner. Thank you.
Just before I close the raffle, tonight we raised $520 for a research promotion. Adam cannot be here, but he asked me to say a few words. So thank you to Joe Delavelle for donating the 2 tickets for the Ottawa Senators versus Detroit Red Wings. So right now I'm going to ask Ryan if he can draw the winning ticket for this evening. your tickets away. Got a ticket. Another blue ticket, 3889142. Oh,
Yes. Thank you.
At this time, I'd like to welcome Ryan up to the stage. So Ryan is our speaker this evening. He is an ASHRAE Distinguished Lecturer, all the way from Saskatoon. So a little bit about Ryan. I know there's a lot of information here, but I kind of summarized the goals over it. So Ryan is the Secretary, Treasurer, and Principal Engineer at the mechanical consulting firm Daniels Wingerack Engineering Limited in Saskatoon. The firm specializes in mechanical consulting or mechanical system design for commercial and institutional buildings, including, is that the Nutrient Wonder Hub?
Yep.
Children's Discovery Museum, Children's Hospital of Saskatchewan, and various other buildings. Prior to joining Daniels Wingerack Engineering in 2002, Ryan was a research assistant and sessional lecturer at the University of Saskatchewan, where he received his bachelor and master degrees in mechanical engineering in 1999 and 2005. Ryan is currently on the ASHRAE Society Conference and Exposition Committee and a member at large on the ASHRAE Saskatoon Board. He has served many other roles with the ASHRAE Saskatoon Board, including past president, treasurer, membership promotion chair, research promotion chair, chapter technology transfer chair. He's also a past regional vice chair for research promotion for ASHRAE Region 11 and general chair for the chapter regional conference, CRC, held in conjunction with the ASHRAE Saskatoon chapter 50th anniversary. Ryan is also involved in many technical committees, too many to mention here. But this evening he'll be talking about hydronic system heat transfer. Heat is constantly being transferred between hot and cold, trying to reach an equilibrium. Understanding the modes of heat transfer and terminology can help make use of transferring the heat to where it is required, either to a fluid or to a space for comfort applications. The relationship between heat transfer and flow are examined and common design issues are presented. The relationship between heat transfer and flow are examined and common issues are presented. The presentation will review heat transfer fundamentals, the relationship between heat transfer flow rate and temperature drop, supply temperature, designing for a high temperature drop, thermal equilibrium, low supply bar temperature, and heat exchanger fundamentals. So thank you, Ryan, for visiting the Ottawa chapter, and welcome. Thank you.
Okay, thank you for that. There was a lot there, and thank you, I'm done. So I have been involved in ASHRAE for quite a long time. Started as a student member, met my future employee partners through the ASHRAE golf tournament, started working for them. They said, you need to go to ASHRAE. Started out as an ASHRAE bartender for our chapter bar. Moved up through all the ranks of the ASHRAE roles, as was discussed. And then through the work at the regional level, got more involved in the society. And now I'm on the society committee on conference and exposition. So if any of you are attending the winter or the annual meetings, I'll probably be stuck in the speaker's lounge reviewing the presentations. So that's the main part of our role at the conference. There's work beforehand to deal with that too. So I am here as a distinguished lecturer. I was just saying to my table that this is my first year being a distinguished lecturer. I have done presentations for our ASHRAE Saskatoon chapter in the past and have spoke at our university as a sessional lecturer, but you are the first chapter in my first year to actually host me as a distinguished lecturer, so thank you for having me here. So first off, ASHRAE is involved with leadership and volunteerism. So we are looking for more volunteers and always looking for future leaders. So if you think you've outgrown ASHRAE, you're wrong. There's more input from you we can gather. Writing handbooks, supervising technical sessions, or presenting to other chapters. So just some people that I've dealt with indirectly to help put this presentation together. They don't know that they've helped me, but they have. Same with some of our photo credits. I didn't take any of the pictures. They all come from various websites and suppliers. So I tried to hide who those came from. Just a quick overview of what we're doing today. Heat transfer fundamentals, how it relates to hydronic systems, the relationship between heat transfer, flow rate, and change in temperature, why deal with hydronic systems, supply temperature, high temperature design, and heat exchanger fundamentals. So if you were here earlier and heard Joel speak, then he gave a good introduction of what I'm going to touch on. Some of it's going to overlap and I'm going to contradict him on some things. Perfect. And if you weren't here, then you have nothing to compare me to, so that's good. So first off, what is heat transfer? So all matter has internal energy generated by the movement of molecules. The amount of internal energy can be labeled as an object's heat. We measure this by the temperature of the object. All systems try to reach a thermal equilibrium by equalizing the temperature of the components with the surroundings. With all energy, the difference in the amount of energy between items is unstable. We want to reach a balance. Heat transfer is therefore dependent on the change in temperature. As we're all aware, in the winter, we can blow in our hands, warm up our fingers. This is a type of heat transfer. But then we can go inside and we have to blow in our hot soup. So that's also heat transfer. So we're blowing cold air on our soup and hot air on our hands. No, we're not a wizard. There's just a temperature difference, right? So other forms of heat transfer that we can relate to, holding our hot cup of coffee will warm up our hands. That's conduction. And holding our hands up to the fire is a radiation. The air between our hands and the fire is still cold, but we can feel the heat through radiation. So starting off on the basics of heat transfer, so conduction is only through solids. Heat transfer, we'll call that as Q, is dependent on a few things. So of course, temperature difference, we mentioned that, a material property, the K value, and the area, and a thickness in the direction of the heat transfer. So combining those, the heat transfer rate is proportional to the area times the material value times the change in temperature divided by the thickness. And we get units in either BTUs per hour or in the imperial in watts. If we rearrange this a little bit, take out the material properties, we can combine all those, the thickness and the K value, and get a resistance. So the heat transfer rate is the area times the change in temperature times the resistance of our material. So the higher the thermal conductivity, the material, the lower the resistance, and the greater the heat transfer, everything else being the same. So for example, if we have wood, the K value of wood is about 0.06 BTUs per hour per foot per degree, and the K value of fiberglass insulation is about 0.02. So we've got a 3-to-1 ratio between wood and fiberglass insulation, which is why if we have a wood frame building with fiberglass, you get cold spots on the wall. You can certainly see that in my house, where I can actually get frost forming every 16 inches. So moving on to some examples of the hydronic systems where these different types of heat transfer can occur. So the first type of heat transfer we touched on was conduction. So a hydronic system with conduction would be in-slab heating or cooling. We have a pipe embedded in the concrete, some insulation on the bottom to stop the heat transfer going downwards, some covering material, in this case it looks like a wood structure on the top. So heat transfer is from the pipe going out. In this case we've got different options for the material, copper or PEX piping within the concrete slab. The K values there for copper and PEX are shown, 227 for copper, and depending on the type of PEX you got 0.243 to 0.295. So the copper heat transfer about 700 to 1,000 times better heat transfer than through PEX. Now, in this case, the direction of the heat transfer is from the pipe up to the surface, and we're dealing with the thickness of a copper pipe or the PEX pipe, so the X value in both cases is very small. So it really doesn't matter if you have copper or PEX within that concrete. The heat transfer medium is really the concrete. Just some examples of some conduction for hydronic systems. So the bottom would be the piping attached to the underside of a floor. In this case, we just got some PEX piping attached right to the floor, and the bottom temperature graph just shows the heat coming out of the pipes, basically going into the space. To make this a little bit better, we can add some aluminum fins or plates to the underside of the trusses. We get a better heat transfer, more uniform between the joists, and the heat transfer on the top temperature graph shows a little bit more uniform and less heat transfer through the air. Moving on to radiant systems, radiant heat transfer. So radiant heat travels at the speed of light. It can travel through air, but we don't need air. It does travel through vacuums, which is how the Earth is warmed up from the sun. It is also by line of sight, so you need objects that can basically see each other, although the heat can be reflected. So this heat transfer by radiant is again dependent on temperature difference, the surface area between the objects, and a material property. This time is called emissivity, on how much the radiation thermal energy is emitted from the property, from the material. So the heat transfer equation for radiant heat transfer, we've got the Stefan-Boltzmann constant, an area factor, a shape factor, a temperature difference to the power of fourth, and the emissivity at the bottom. Some examples of hydronic systems with radiant heat. So in-slab heating or cooling, again, we've got a big mass of heat or cool below us, and that acts as a radiant surface within our room. The slab is at a different temperature than the surroundings. A more common one would be a gas-fired radiant heater. The gas combustion is through the tube, creates a hot tube, and heats up the space. You usually see these possibly in arenas, over top of the stands, or warehouses, or overhead doors. These can be hydronic, but they're usually a gas or an electric heater. More common type of hydronic radiant system is radiant panels. These can be heating or cooling. So similar to the underfloor panels, we have some piping attached to aluminum plates. In this case, the tubing is mounted on a wall or in the ceiling to get our heat transfer. We do need to have good conduction between those copper plates or the copper tubes and the aluminum plates. So we usually have a heat transfer paste attached there to have that conduction part useful. And similar to the under slab we are looking at, we need to have insulation on the top of this so the heat isn't going up if this is a ceiling mounted panel. Another type of radiant heat for a hydronic system is called a radiator. So the name comes from the fact that the radiant heat comes out of a big source of material that holds the heat in. So typically a cast iron radiator, this can be a steam system or a hydronic system. It'll be over in the corner of the room and just get hot and radiate the heat out to the room. These are sometimes called convectors, but we'll touch on the convection part here. So convection is the third type of heat transfer. Deals with the motion of a liquid or a gas. We can have either natural convection or forced convection. So natural convection is only dealing with buoyancy, and forced convection is dealing with motion, so a pump or a fan. Again, heat transfer dependent on temperature difference. That's all heat transfer. And temperature difference in area and fluid properties. So density, velocity, specific heat of our materials. The equation for convection heat transfer is a heat transfer coefficient, which is H, the area, and the temperature difference. Just a range of some heat transfer coefficients that you can see. Natural convection with air, fairly low, 1 to 5. Forced air, 2 to 10. Forced water, 20 to 3,000. And boiling water, really good at transferring heat, 500 up to 5,000 all imperial units, BTUs per hour per square foot per degree Fahrenheit. These aren't the actual conversions between the imperial and the metric. If you need to know that actual conversion, you can talk to me later. So convective heat transfer, again, one good example is in-slab heat. I'm not trying to sell in-slab heat, it's just a really good example of all 3 modes of heat transfer. So most heat transfer does involve all 3 modes: convection, conduction, and radiation. For the in-slab heat, we have forced heat transfer of the pipe, the fluid, the water through the pipe, and we have natural convection of the air above the surface. It heats up and moves away. Baseboard or wall fin heaters. We have pipes flowing in the tubes with some aluminum fins to enhance that heat transfer. The air passes over this, again warms up and moves out of the way. Or a passive beam using the cooling method. The cooled air, or the air passes over a cooling coil and moves down out of the way to cool the room. Water flow inside the tube. Tube has fins to help with the heat transfer to the air. More convection type heat transfer units, convectors or force flows, unit heaters, fan coils, sometimes called cabinet unit heaters. On the cooling side, we also have active beams. So water flows inside the tube. We have a coil or a fan, or water flows inside the tube or a coil, and a fan moves the air over that to enhance that heat transfer. Active beams require an outside fan source. So manufacturers of this equipment have usually already figured out their heat transfer characteristics of the equipment. And I'll give you that in the data. So a typical example based on one manufacturer of heating equipment. So for 1 foot of hydronic wall fin on heating output, about 1,700 BTUs per square foot, with entering water at 170 degrees. Whereas a 54-inch wide cabinet unit heater, so we have a fan inside on the air side, get up to about 100,000 BTUs per hour output. So much larger output with the fan involved. So certainly when we're dealing with hydronic systems or all heat transfer systems, we need to be aware of all modes of heat transfer: conduction, convection, and radiation. At room temperature, our body is always losing heat. Our body is always hotter than the air we're in, unless we're in Phoenix in the summer, and we don't feel very comfortable. So our thermal comfort is dependent on the air around us and our surface temperatures around us. So one example that we can think of, we're in this room, the air temperature is 22 degrees, we're generally feeling comfortable. If we take the same air temperature, 22 degrees, but we're in a glass box outside in February, the air temperature is still the same, but now we have 4 or 6 surfaces of glass all around us, with the air temperature being outside in Ottawa winter. So we feel colder from the radiation, even though the air temperature is the same. So moving on to the hydronic heat transfer part. So all the equations so far are dealing with the heat transfer between the materials at different temperature. But if we want to isolate only one part, only the air or only the water, we need to go back to laws of thermodynamics. So energy is conserved between these systems. We describe the internal energy is the measurement we use for temperature of the object. So our internal energy plus our heat transfer is our final internal energy, assuming we're not doing any work. So our internal energy is our U, our heat transfer is still our Q, and our final amount of internal energy or temperature of our system. So the change in internal energy we can measure by the enthalpy of an object, which is the internal energy plus the pressure times the volume. And no changes of volume or pressure, then our enthalpy change matches our internal energy change, H equals U. And we get the mass times the specific heat times the temperature to give us the enthalpy. The specific heat is the amount of heat required to change one object 1 degree. So 1 BTU per hour is the amount of energy required to heat water, 1 pound of water, 1 degree Fahrenheit. We have been dealing with our heat transfer units in terms of BTUs per hour, or joules per second, which is watts. And our H, we need a flow rate. So the mass flow rate times specific heat times the change in temperature gives us our change in energy. So the mass flow rate, usually pounds per hour or kilograms per second. How do you measure mass flow rate? You usually don't measure how much pounds of something is coming out. We measure a volume. So gallons per minute would be a normal measurement for a volume flow rate instead of a mass flow rate. So a quick unit conversion is trying to get from our gallons per minute to something that we can use in our heat transfer equations. 1 gallon per minute, 60 minutes an hour. There's 7.48 gallons per cubic feet. We get a unit conversion of 8.02 cubic feet per hour. We also need to remember we need to deal with pounds. So we need to know the density of the object we're dealing with. So the 8.02 was our unit conversion times our GPM times our density. That goes back into our equation, so the mass flow rate times Cp delta T. So for water at 70 degrees, the density is 62.3 pounds per cubic foot. Our specific heat is 1 BTU per pound per degree Fahrenheit. So 8.02 is our unit conversion, times our GPM, times 62.3, times 1 times delta T. If you're good at math, you figured this out already. If not, maybe you remember what Joel had said. You combine all these, 499.646 GPM delta T. So Joel just presented it, and the students here presented it 500 GPM times delta T. Close enough. But be careful, that was only water at 20 degrees. So density changes and specific heat changes. There's a quick graph there to show the temperature or the density changes as we change the temperature of water. So it's not always 500 GPM. Certainly, if we have glycol or we're dealing with something else, go back and check that base equation with density and specific heat. If we look at air, density is obviously a lot less than water, 0.075, and our specific heat is a lot less, 0.24. Going back to that base equation, mass flow rate times specific heat times change in temperature, plug it all in, 1.08 times the CFM times the delta T. Joel just rounded that off to 1.1. So again, probably close enough. Check what conditions you're dealing with. So if we're dealing in metric, because we are Canada, we need the flow rate in kilograms per second. We usually measure our volume flow rate in meters per second. We have the density of water, the Cp of water, our density of air, and the Cp of air. We can get the equivalent equations in metric. 4.17 times liters per second times the delta T in Celsius for water, or 1.21 times liters per second times delta T for air. And this is dry air only. Once we add in water and humidity, then those equations do change. Works for heating, not necessarily for cooling. So just a quick review of those equations for water and air. These are kind of the basis for hydronic heat transfer. If we're dealing with moisture, go back to the change in enthalpy. So the enthalpy values for air systems do change at different temperatures and pressures. So what's a common temperature drop for hydronic systems? Someone told me this afternoon, 3 degrees. Seemed really low to me. I'd suggest maybe 20 degrees Fahrenheit, more common. Why? Why do we use 20 degrees? Easy to calculate. Remember 500 GPM delta T, where delta T is 20. Now we're down to 1,000, oh, that should be 10,000 BTUs per hour per GPM. So it makes the math easy. A good basis of design. Sometimes. There are certainly lots of systems designed around 20 degrees delta T, Fahrenheit. So using some of that, just a quick math test. Temperature drop of water, flowing half a GPM to provide 500 or 50,000 BTUs of heat. So our equation, heat transfer of water, 500 delta T times GPM. Rearrange a little bit to isolate our delta T. Easy math, 200 degrees. Not a problem, right? So, engineering test. Can we have a 200 degree delta T? Water freezes at 32, 200 degrees above that, 232, so you're going from steam to ice. Not very practical. So what do we do? Can we increase that heat transfer rate? Increase the flow rate? Yes. There is a limit to the change in temperature we can reach by increasing the flow. So even though we increase the GPM, the change in temperature might decrease, not in proportion. So there is an actual limit to the amount of heat transfer available for a situation. So a quick little diagram, we've got some flow, hot water through a baseboard, 180 degrees water, 1 GPM, we're getting about 35 degree temperature drop through this, even though it's about 17,000 BTUs per hour heat output. Double the flow up to 2 GPM, our temperature drop has gone from 35 to about 12, 11 or 12. Our heat transfer out of our wall fin has gone up to 22,000 BTUs. So 16,000 to 22,000 by doubling our flow rate. Try and double it again. Our temperature drop is down to 6 degrees, and our heat transfer output has only gone up 22,000 to 23,000. So we're reaching the limit that this heat transfer medium can handle for our flow. Again, using one of the normal manufacturers that we deal with, just their charts of conversion factors of heat transfer for various flow velocities. Down at 0.1 meters per second, we're at about 90% of what their rated capacities are. Rated capacities are based on a velocity of 1 meter per second. And then as we increase, the heat transfer output slowly increases too. Another manufacturer on the fan coils on the right. So if normal situation is the 1 GPM flow rate, you can see as you increase the flow rate, there is a limit to how much heat transfer you get off. But also as you decrease the flow rate, it can drop off quickly. So there is a normal point to design the systems around. You can't make your flow rate too fast for heat transfer, but you can make your flow rate too fast for practical purposes. Noise and pressure drop are a concern. So some typical maximum flows for noise, 4 feet per second. For pressure drop, 4 feet per 100. So I'm glad those numbers agree with Joel presented earlier. So why do water systems, why do hydronic systems? So Joe mentioned that water systems are around and we are familiar with the way water works. Water is a very good heat transfer medium. We saw the CP values between water and air. The water has much greater heat transfer capability than air, so it's easier to put smaller pipes through a system than larger ducts to get the same heat transfer. We have lots of equipment choices when we're dealing with hydronic systems. There are lots of manufacturers out there dealing with heating water or cooling water. Water is safe, typically available. It's not become too scarce yet, so we can get water just by opening up the tap, fill up our hydronic system. If we have a spill or a leak, again, we just turn on the tap and refill it up. We don't need to call someone with a special canister of water. Easy to make piping changes, so we're not relying on a special trade, a refrigeration tech, to make small copper tubing piping changes. Almost any plumber can fix a piping system. Don't trust them. There's also not much dependency on refrigerant gases on the whole climate change. If we're dealing with a VRV, VRF system filled with refrigerant, does the law change that that refrigerant is no longer available in the future? Also easy to provide zoning and make changes to the system. If we're dealing, again, with a refrigerant-based system, we may not be able to expand that without changing a lot of aspects. So some of the equipment that we need for a hydronic system heat transfer, so chillers or heat pumps to generate chilled water, boilers to generate hot water, absorption chillers, use some heat to generate cooled water, conduction through our solar systems, and there are heat recovery options available where you can transfer heat between them. Sometimes we do need refrigeration cycles when we're dealing with generating cold water or chilled water. It can be combustion or direct heat transfer. So we talked about a 20-degree delta T as a normal supply temperature or supply temperature drop. What is a normal supply temperature? Depends what we're trying to do. So heating systems, these are all degree Fahrenheit. 210, 180, 160, 110. Cooling, 45, 60, maybe even 25. All depends what we're trying to do. Domestic hot water production, we need over 160 degrees Fahrenheit. So originally, 210 degrees was based on wood-fired boilers. Throw the wood in, heat up the water. You got the fire so hot you're turning into steam. It's usually an open system. The steam just escaped out the top of the fireplace, so you'd have to take some wood out. So not very good temperature control by pulling out hot logs out of the fire after the fact. Also, those older systems needed a lot of temperature in the water to have natural convection to force the water upwards through the rest of the building. Since we moved away from wood-fired boilers, we've gone to natural gas. Gas is easier to control, and therefore the burning process is easier to control. And controlling the burning process, we can control the water temperature. There's still a lot of heat output, so we went with 180 degrees as our supply temperature. More recently, we've moved away from the high temperature boilers, better control, better efficiency. We want low temperature boilers. We can handle return waters down below 130 degrees to get some condensation and get some extra efficiency. So now the systems were maybe designed with 160 degree water temperature with over 30 degree temperature drop to get that return temperature down to 130. And now more recently, we're trying to do that same heating with lower temperature water. Lower temperature supply water, we need larger surface area, but lower return temperature, we get better efficiency out of our boilers. So the 130 degrees mentioned there is a magic number. That's where the condensation starts to occur in the flue gases of natural gas, depending on the amount of oxygen we have in our burner. Somewhere between 130 degrees and 134, depending on the mixture of the oxygen in the burner. We are also becoming more concerned about releasing carbon into the atmosphere. So we certainly want to be better efficient on our systems. We don't want to be cutting down trees for our wood-fired boilers or burning the natural gas for our burgers. So just a typical boiler efficiency curve. So up at the higher temperatures, 160 and above, kind of get a maximum efficiency of about 87%. As the water coming into the boiler drops, we can get an increase in that efficiency, all the way up to 100%. If water is 70 degrees, we're trying to make 70-degree water, we can just turn the boiler off and it's 100% efficient. So we want sometimes a high supply water temperature, but we want low water return temperature for our boilers to be more efficient. So we can do this just with a larger temperature drop. So instead of 20-degree Fahrenheit temperature drop, something larger. Europe has been designing around 20 degrees Celsius, 36 Fahrenheit, for quite some time. Or to go back to the imperial reason why we use 20 degree, to make the math easy, why don't we do metric math easy? Our water is 4.17 times delta T times liters per second, gives us our kilowatts. So at 25 degrees Celsius, 45 degree Fahrenheit, gives about 100 kilowatts per liter per second. Almost the same easy math as the imperial, but a very large temperature drop. A lot of systems I'm seeing have a 40 degree Fahrenheit temperature drop. It's about double the BTUs per GPM that we're seeing in the older systems. So high change in temperature design, large temperature drop, lower flow rates, smaller pipe sizes, smaller pump requirements. And Joel had mentioned some of the pump laws. So our ratio of our flow equals the ratio of the speed, so the RPM. The ratio of RPMs equals the ratio of GPM. The pressure is related to that ratio squared, and the power is related to that cubed. So if we reduce our flow, we reduce the system power. Smaller flow gives larger delta T, but smaller pipes and smaller pumps. So as Joel mentioned, we need to do some sort of cost analysis to determine where the right size is for the pumps and the pipes and the energy use. We talked about a maximum flow earlier for noise and pressure drop concerns, but you do also have to be aware of the minimum flow. If the water's not flowing, you've just got conduction. So, modifying existing hydronic systems, going into an old building, saying they've got an old steam system, what do we do to change this, upgrade it to a hydronic system with today's technology? So, I always think it's a good idea to start back at the heat loss calculation of the building, of the system. So there have been any changes to the system? Envelope, insulation, windows, change in use. So less people, more people, changes the amount of outside air. Try and figure out what the original conditions were. 180 degrees, 20 degree delta T. Find what the new average temperature can be to meet that heat load. Hopefully it's different than the 180. Otherwise you can't change much. Review that temperature condition, see if it's acceptable for a larger delta T to get to the efficiency of the new equipment. Usually we can't get a high enough change in temperature through this though, so we need to do something else. Certainly if we want to use condensing equipment year-round. So back up, pick a temperature change that you want to work with, and redo the design selections based on the terminal units, so the wall fins, the fan coils, with that new temperature. Just a quick relationship of the building envelope changes, so that's the Q new versus the Q existing. So a linear relationship between the amount of heat transfer and the temperature difference between the rooms. Just shown as a quick graph. Originally we were designed at 180 degrees. We did some improvements to drop the temperature from 100,000 BTU temperature loss to 70,000 BTUs heat loss, our supply temperature can drop from 180 to 147. So in that case, we're talking about possible envelope improvements, so the added insulation in the attic and the walls, new windows. So with the new supply temperature, then you need to review all the existing terminal units for the output at the new average temperature. For example, if we have baseboards around the perimeter, we don't in here. So baseboards around the perimeter, check out that length, figure out what your heat output is on each of those new temperature. Figure out what your total length is required of wall fin. Might be the same length, you get the right output, or you might need more. In some cases, you might need to double the amount of heat you're adding to the space because you've dropped the temperature so much. That might not be practical, so you may want to look at something different than the baseboards that you have there. Maybe that convection heat transfer, so radiator, fan coil, that type of stuff. Determine how many more heating units are required, either the same style or different style. Also, you can look at the piping. If the piping's in series, we have the hot temperature going through the first units, and slowly the temperature is dropping as we move throughout the rest. We can revise that so we get hot temperature water to all the systems to start. Touching on heat exchangers, how do the heat exchangers work? So we've been dealing with the heat emitters, so the actual parts within a room that transfer heat from the fluid, the air, or the water usually, to the room. We have various types we talked about in the convection, radiation, conduction portion. The heat exchanger transfers heat between the fluids, so air to air, liquid to air, liquid to liquid. Some example of a gas to liquid heat exchanger could be within a boiler, or we get refrigerant to water in a chiller. Could also have a steam to water heat exchanger. Three main types of heat exchangers: shell and tube, coil heat exchanger, and a flat plate. Just a quick schematic on each of those. So the tube, we have some tube bundles within an exterior shell. These can be usually horizontal or vertical. And straight tube, U-tube, usually the end can be removed so you can clean off the tubes and get better performance. A coiled heat exchanger, usually you would see this for domestic hot water production. Some sort of coil on the inside wrapped around with the fluid on the outside. In the case of domestic hot water production, we have the boiler water flowing through the coil and the domestic water in the main tank. And a flat plate heat exchanger. So a couple main types, plate and frame. All the plates are usually bolted together to create the heat transfer surface, or we can also get a braids plate where they're all physically attached to each other. Just a quick graph of how the heat exchanger temperature works. We can have parallel flow or counterflow. Most temperature heat exchangers are designed as counterflow because we get better heat transfer through them. Parallel flow would have the coldest water entering at the hottest water on the hot side, where the counterflow, it's the opposite direction. So the heat exchanger performance is based on temperature differences. Again, temperature difference is what drives heat transfer. In this case, we have the area of the heat transfer and a log mean temperature difference between the hot and cold fluids. And this U is not the internal energy, it is a heat transfer coefficient between the heat exchanger, combination of convection on the cold side, conduction through the heat exchanger walls, and convection on the hot side. If you're an equipment manufacturer, you can determine this by experiments or using math going back to those base equations on convection and conduction. This heat transfer coefficient can depend on the fluid, the flow rate, and the temperature. The heat exchanger area, again, you can get that from the manufacturer, how much surface is actually in contact between the two. So heat exchangers always have some sort of penalty for going through the heat exchanger. You very rarely can get the outlet of the cold side to match the hot side. Usually the selection of heat exchangers is done by software from the manufacturer. And there can be fouling inside the heat exchanger which will reduce the heat transfer capabilities. Our temperature difference in this case is called a log mean temperature difference. It's a relationship between what's coming in and what's going out between the two sides. And just how it's graphed there, the temperature change 1 is the one side of the counterflow, temperature change 2 is the other side of the counterflow. So a quick summary of what we've gone over. So basics of heat transfer, conduction, convection, radiation. We have some examples of hydronic heat emitters in slab, baseboards, radiant panels, force flow units, fan coils, passive beams, active beams. Developed all the heat transfer equations for air and water, metric and imperial. With those you can find a temperature difference if you know how much heat you're putting into something, or how much heat you need to get a temperature rise that you want. Talked about condensing boilers, large temperature drops, changing hydronic systems, touched on that a little bit, and a little bit on heat exchangers. So that's all I had as an overview of hydronic heat transfer. So, any questions?
Questions for Ryan?
I'm curious to know where you and Joel disagree.
The main part was, the main part in my mind is Joel threw out the 500 delta T GPM. So that
I was being expeditious.
so the 500 GPM delta T is a good rule of thumb based on water at 20 degrees Celsius. So if we're dealing with glycol, dealing with higher temperature water, that 500 does not apply. So we need to be aware of that. It does not apply all the time. Certainly if we're changing from normal temperature water, go back to final density and the specific.
Well, we both agree with great review.
I have not seen them without, so
Trust me.
okay.
So what would be the high temperature point where you would say this is no longer a good estimate? In terms of hydronic systems, like if I'm still working with 180, is that still okay, or would you say this?
So it would depend on how accurate the rest of your assumptions are. So we have the chart there of the temperature range of the density changes. And certainly if you have any glycol in the system, that can go down to as low as 420 instead of 500 as being the constant. So it's good to know what your average temperature is in the system and go back to that base equation with the density and specific heat. So there's the chart of the temperature change. So the 62.3 is water at 20 degrees Celsius, 7 degrees Fahrenheit. So between 70 degrees Fahrenheit and maybe 130, that's not changing by much, right around the 62. So usually the rest of our hydronic system building envelope calculations are less accurate than that. So if we're getting down to 490 as the constant, that's not going to change much in the overall design. But when you get to the larger temperatures, 200 degrees Fahrenheit, or the cooler temperatures down to 50 for chilled water, then that can have a greater effect.
So as you reduce the supply water economically, where do you feel that realizes what is your kind of rule of thumb you would say that's kind of where you want to?
Well, again, with the question was, where do you find the trade-off between smaller pumps, smaller pipes, and larger terminal equipment? So with a lower temperature supply of water, you get better efficiency on your boilers, but your heat emitters within the room need to be larger. So unfortunately, all of our heat emitters come from something that we've mined. Usually it's copper and aluminum coming out of the earth. So there is not only an economic cost to making our terminal units larger, then there's the material cost coming out of the unit. So Europe's been designing around the 40-degree Fahrenheit temperature drop. They always seem to be knowledgeable in that type of stuff. So that certainly seems to be a reasonable temperature drop in my mind. The equipment in the room is not too big, and we are getting some benefit of the smaller pumps and the pipes. If you got free baseboard, build it at the lowest temperature you can go. Kind of avoided your question.
Well, I did simple answer.
Yeah, no simple answer. It depends on your electricity costs. How much electricity are you actually trying to save? With a move to a more carbon neutral environment, then maybe we are more looking at reducing that horsepower, and we can use larger equipment within our spaces. So some of it has to deal with our architects on how much ceiling space they'll give us, how much wall space they'll give us for heat emitters, or room for pipes. So no fixed answer, but I like the 40-degree Delta T. That's a good temperature drop for our room side heat emitters.
Any other questions? All right. Well, thanks again, Ryan, for coming down to Ottawa.
My
On
pleasure.
behalf of the Ottawa-Valley chapter, we have a small parting gift for you.
All right.
Take back to Saskatoon. Thank you very much. If you guys want to hear more about Ryan, we'll be at the Master's office tomorrow delivering this seminar. So there's a few spots left if you do want to attend. The link is still available on the website. To wrap things up, our next meeting is here, November 19th, and the topic is transcritical refrigeration systems with CO2. And the speaker is Frederick Adelaide Trubiano. So with that said, there will be a survey going